Okay, let's use the graph y is equal to g of x to determine each of the following. So we're going to be using limits to identify if the point is continuous or not, right? So let's look at part A. Limit as x approaches -2 from the left, g of x. So this is a left-handed limit. You're approaching -2 from the left side, so you're basically going this way. You can see that there is a hole here. This is a point that doesn't exist. It's also known as a point discontinuity. And because you have a point discontinuity, this value actually doesn't exist, so we just write D and E. Okay, let's look at part B. We're looking at the right-handed limit of -2. So -2 from the right side. -2 from the right side, you can think about this as like negative, like you're approaching -2 this way, right? So you can think about this as like -1.9999, right? So if I look at that limit, basically going this way, you can see that it approaches the point discontinuity, which is the hole, right? So once again, this doesn't exist. So because the two left and right-handed limits don't exist, right, then we can already kind of assume here that this point is discontinuous, right? So the left-hand limit of -2 of g of x is equal to the limit, the right side limit of g of x, which is equal to doesn't exist, and this tells us that x should be discontinuous at -2, right? Remember that we need to fulfill all of the criteria. The left-hand limit has to be equal to the right-hand limit, which has to be equal to a finite value, which also has to be equal to the original limit, right? Which also needs to be equal to a finite value. So both of these don't exist. Right. Now let's look at the original limit as x approaches -2 of g of x. Now, as x approaches -2 of g of x, you actually have a point here, right? And if we solve this limit, it's basically g of -2, which we can actually solve as 1, right? So both of these cases would be 1 because g of -2 is equal to 1. And we're using the limit property, limit as x approaches a, f of x is equal to f of a. In this case, f of a is equal to L, right? That it's a finite value. However, because the left and right-hand limits don't exist, then this point is discontinuous at -2, that there is a break at -2. And because you have a point and you have this hole, this point discontinuity, this is what we call a jump discontinuity. Okay, so this is what we call a jump discontinuity. Okay. And this basically implies that there is a break in the function. Okay, so as a result, therefore x is discontinuous at x is equal to -2, right? And usually jump discontinuities, you can see that the left and right-handed limits are going to be, they won't exist. Okay. Now that was for the testing of -2. Let's take a look at testing 1, right? So if we're looking at 1 from the left side, okay, so limit as x approaches 1 from the left side. If you're approaching 1 from the left side, this is 1, you're approaching it this way, the g of x here is equal to 0. Okay, if you're approaching 1 from the right side, let's say limit as x approaches 1 from the right side of g of x, you can notice here that you're going this way towards 1, and g of x is also equal to 0. So the left and right-hand limits are the same, right? So it does exist for the time being. Now let's take a look at part G. Limit as x approaches 1, g of x, if you use the limit property, is equal to g of 1, which is equal to 0. Okay, so both of these cases are equal to 0. So this implies, and we can write a final statement here, right? This implies that therefore the limit as x approaches 1 from the left side, the left-handed limit is equal to the right-hand limit of 1, which is equal to the original limit as x approaches 1 of g of x, which is equal to g of 1, which is equal to 0. So therefore x is continuous at 1 and 0. Okay, so that's the proof that we would want to write using limits, right? So limits are really useful in determining continuous points, and also the presence of discontinuities, and we looked at the jump discontinuity.